Welcome to this explainer where we're going to completely demystify UART. We'll be starting off with a really simple, fun analogy and then zooming all the way down into the intricate, glowing pathways of modern microprocessor architecture. Whether you're a total beginner or an aspiring hardware engineer, we are going to break this whole thing down for you.
Okay, let's just dive right into this by asking a pretty fundamental question. How do devices actually communicate? I mean, if two electronic devices, like your CPU and a sensor, want to talk, they could theoretically use 8 separate wires to send a whole byte at once, right? But that takes up a ton of physical space. So how do they manage to do it using just a single transmission wire?
Well, here is our roadmap for today to figure that out. First, we'll meet the UART postman. Then, we'll unpack the UART envelope, take a look inside the hardware, explore UART in modern SoCs, compare some communication protocols, and finally, we'll wrap up with testing and verification.
Let's hit Section 1. Meet the UART postman. We really need to establish a solid, simple mental model for how this communication actually works.
So the absolute crucial point here is that UART stands for Universal Asynchronous Receiver Transmitter. It's a hardware protocol that essentially only needs 2 main data wires to work, a transmitter wire, or TX, and a receiver wire, or RX, plus, a common ground. It sends data serially, which simply means it's sending it 1 bit at a time.
To really visualize this, I want you to imagine UART as a friendly neighborhood postman. This postman carries just 1 letter, representing 1 single bit of data at a time from one house to another. The transmitter house sends the letters out, and the receiver house gets them. It's a brilliant system, really, because it allows devices to talk back and forth without the expensive, bulky need to send all 8 bits at once on multiple parallel wires.
Moving on to Section 2, unpacking the UART envelope. What's super interesting here is how we package those letters for secure delivery. Because, well, we aren't just firing raw data down a wire, we have to format it properly.
You've probably noticed that the A in UART stands for asynchronous. Now this means there is absolutely no shared clock wire connecting the two devices. In synchronous systems like SPI or I2C, there's a dedicated clock wire ticking away to keep both sides perfectly in sync. But since UART is asynchronous, both devices must strictly agree beforehand to send and receive bits at the exact same speed. And we call this agreed-upon speed the baud rate.
Because there's no clock wire to shout, "Hey, here comes a new letter," UART wraps the data in a protective frame. Think of it kind of like a data envelope, or maybe even a little colorful train. It always begins with a start bit. Normally, the line is just resting at a high voltage, but the transmitter pulls it low to announce, "Hey, a new character is coming." Then comes the actual payload, which is usually 5 to 8 bits of data. Next up is an optional parity bit, acting a bit like a teacher counting students on a field trip, just to make sure no bits flipped by mistake during travel. And finally, 1 or 2 stop bits pull the line high again to signal the end of the character.
So, let's watch the exact sequence of how a character, let's say the letter A, is physically pushed across that wire. The ASCII letter A is converted into the binary sequence, 01000001. As these glowing data packets move bit by bit down the wire, first that start bit drops the voltage. Then our binary A flows right on through, followed by the parity check, and finally the stop bit resets the line. All right, Section 3, inside the hardware. Let's look at how this physically works. What does the factory inside the transmitter actually look like?
Think of this whole flow like an automated assembly line. First up, the CPU drops the data off, but it can't just toss it haphazardly onto the wire. A highly accurate block called the baud-rate generator creates these incredibly precise timing pulses. Then, the transmitter hardware takes the data, adds our start and stop bits, and shifts it out serially onto the wire, perfectly timed to that baud rate. Over on the other end, the receiver is eagerly watching. The second it sees that start bit, it uses its own timing to sample those incoming glowing bits, reconstructs the letter A, and simply hands it over to the receiving CPU.
Now, as you probably know, CPUs are fast, like incredibly fast, way faster than our little UART postman. To prevent the CPU from just standing around waiting, UART uses a FIFO, which stands for first in, first out. Going back to our analogy for a second, you can think of FIFOs as the postman's mailbag queue. The CPU can drop a huge stack of letters into the TX FIFO and just walk away to do other things. The UART will deliver them one by one. Similarly, the RX FIFO neatly stacks all the incoming mail, so the CPU can just grab it all at once when it's ready. It's a great way of ensuring letters are delivered in the exact order they were received.
Moving to Section 4, UART in modern SOCs. We're zooming in even deeper now to see how this postman system operates inside a complex, futuristic semiconductor landscape.
Inside a massive modern SoC, the CPU doesn't wire directly to the outside world. Instead, it communicates with the UART peripheral through an internal digital highway, typically something like an AXI to APB bus bridge. Here, the UART acts as an APB slave. The CPU controls the UART by reading and writing to very specific memory-mapped registers. For example, it'll write to the control register to enable the UART, the baud register to set the transmission speed, and the data register to send the actual payload out to your PC, a Bluetooth module, or maybe a GPS sensor.
Now, how do we handle that incoming data efficiently? Well, without interrupts, the CPU would have to constantly poll the UART, literally just asking, is there mail? Is there mail yet? Over and over. That wastes a massive amount of processing power. So instead, the UART generates a hardware interrupt. It essentially taps the CPU on the shoulder and says, hey, I received something. This interrupt system is an absolute game changer because it frees up the CPU to do other critical tasks until the precise moment a new data packet arrives in the RX FIFO.
And when we're talking about truly massive data transfers, we bring in DMA, or direct memory access. Imagine you have a continuous stream of data flowing to a Wi-Fi or Bluetooth module. Having the CPU manage every single byte of that would create a huge bottleneck. So DMA acts as an automated conveyor belt. It automatically grabs data from memory and feeds it directly into the UART's TX FIFO, bypassing the CPU completely. The CPU literally just sets up the transfer and can go to sleep or work on something entirely different.
Section 5. Comparing communication protocols. Let's see how our UART postman actually stacks up against other popular communication methods you're bound to encounter.
When we lay these out side by side, it's pretty clear why UART remains incredibly popular. It has this elegant two-wire simplicity. While SPI is for sure faster, it requires 4 or more wires than a dedicated clock. I2C only needs 2 wires, yes, but its protocol is significantly more complex to implement and debug. UART just sits right there in the sweet spot. It's simple, requires no clock wire, and is absolutely perfectly suited for medium-speed, point-to-point communication. And finally, Section 6, Testing and Verification. How do engineers actually guarantee that these intricate SoC systems work perfectly before billions of these chips are sent off to be manufactured? Well, verification engineers, especially those using advanced methodologies like UVM, run a rigorously strict checklist on the UART hardware. They aren't just checking if it works on a good day, they deliberately try to break the protocol. They'll actively inject parity errors to see if the hardware actually catches them. They'll completely flood the RX FIFO to ensure it triggers an overflow alert gracefully rather than just crashing. And they validate that every single hardware interrupt fires exactly when it's supposed to. They have to ensure that UART can handle the messy, error-prone real world of flipped bits and mismatched timings.
Take this number, for example, 115200. This is one of the most common baud rates, meaning 115,200 bits per second. Engineers must perfectly verify the baud rate generator's timing calculations against the main system clock. Why? Because if the UART's internal clock generation is off by even a few tiny percentage points from this target speed, the receiver will sample the data at the exact wrong time, and your entire payload will be corrupted into total unreadable gibberish.
So, there you have it. We've journeyed all the way from a simple cartoon postman carrying single letters right down into the depths of a high-tech system-on-chip utilizing DMA and hardware interrupts. Whether you're debugging a basic temperature sensor or designing the next major microprocessor, understanding UART is just an essential, foundational skill for any engineer. So the only question left to ask is, what world-changing device are you going to build with it? Thanks so much for joining me on this explainer, and I will catch you in the next one.